And you're going to talk about, I think, about uniqueness of the Martingale problem and the link to energy solutions, right?
Yes.
So,
yes.
Please.
Thanks. Thanks. Yeah, let me quickly recall what we did last time, because it's already 2 days ago and it was late in the evening and a lot of material to digest. So we started with a white noise measure, and there we did the Vena chaos decomposition. So we identified L2 under this measure with a Fock space. On that Fock space, we had these sort of Sobolev spaces, which measured the decay of the the regularity of the kernels in your expansion and the decay of the expansion in N. So you had a sequence of kernels, and each kernel this here would, for example, mean that each kernel is in H minus 1/2. So there was a weird thing with a 2 here, and that this thing is decaying like N to the minus beta, I guess. In N, the nth kernel, the L2 norm of that, or the H minus 1/2 norm of that. And then we constructed the generator of this Kpz equation as an operator mapping to distributions on the Fock space. So this was given as L0, which is this thing here. Okay, so the linear part of the dynamics associated to that, and then the G, which is associated to the Kpz part of the dynamics. And we saw that if you take somehow a usual phi, like a cylinder function or something which has a simple chaos decomposition, then L of phi is never a random variable. It is always just some generalized function on this Fock space. It has negative regularity, which comes from this operator here. So this operator, if you plug in some usual test function in it, it spits out a distribution. And therefore we cannot really work with that. We want to get some functions which are mapped to functions again. So we want to construct a domain which is mapped to functions. And we did this by solving such a modified resolvent equation. It's a proxy for the resolvent equation, essentially. So it would be more or less the Poisson equation. It would be the Poisson equation if we wouldn't have this projection here. This was the projection onto the large Fourier modes. And it's parameterized by the right-hand side. And if we solve this equation, then L of the solution, you just plug in this expansion here. You see that this is L0 of this guy, but this guy we choose, so we just choose it so that L0 of it is in L2, plus some G lower. And in G lower, we only have small Fourier modes. All the large Fourier modes are truncated out. The large Fourier modes would be in G upper. And by going to small Fourier modes, we remove the divergence, and now everything is really in L2. And in this way, we constructed the domain. Once we had the operator in the domain, for which we already had to work quite a lot, we went to the Martingale problem, and we said a process solves the Martingale problem if it is absolutely continuous with respect to the white noise. And this thing here is a Martingale for all functions in the domain. Why do we need this absolute continuity? Well, because these are L2 functions, and you cannot evaluate an L2 function pointwise, but if you plug in an absolutely continuous, if you plug in an absolutely continuous function into an L2 function, this still makes sense. So there's the question by Milton. Well, I said no paracontrolled calculus, but the controlled philosophy is still there. Yes, yes. So the philosophy is very much inspired by all this progress in paracontrolled analysis or regularity structures and all that. So we heavily use the linear part of the equation, or here we see it. We heavily use this guy to control this guy. If this one wasn't here, we couldn't do anything. So yes, we even called these sort of functions controlled, because they have a very specific structure which guarantees that they're mapped to L2. And what happens is that, well, this thing does have some singularity actually. So if you apply the okay, now let me rather say here, so if we apply this operator to such a phi, then we do have a singularity from this part, and we do have a singularity from this part, and both of them are singular, but then they're prepared exactly so that there's a cancellation and all the singular parts cancel, and in the end we remain with something which is nice. Yeah, and then we were talking about the existence of the Martingale problem. For this, we used these Galerkin type approximations. So we looked at this equation, which basically is a Galerkin approximation. We truncate the Fourier modes here, except we don't truncate the noise. This has the advantage that the generator of this is L0, the full linear operator, like the same L0 that we see in the limit, because, well, the linear part of the dynamics is unchanged. And then plus GM, and this GM is a regularized version of our Burger's nonlinearity. And we saw that you can prove tightness by this forward-backward Ito trick. And we saw that any limit point is an energy solution to Burger's equation. So energy solution, let's quickly recall that. That's the last slide with which we ended last time. So energy solution means that you plug in, so we take a test function on the state space of our process. The state space of our process are the distribution on the torus, S prime. And the test function is just defined as integrating or testing our distribution against a smooth function f. And then we evaluate that and we subtract the initial condition, the regular part of the drift, and then somehow this thing which is defined as a limit. And then we get a martingale, and the martingale has the right quadratic variation. Okay, so all of this we had last time, and now what should be next? Well, we still didn't address the existence of solutions to the Martingale problem, right? Right now, basically, concerning the Martingale process, I presented you the state of the art until 2013. But now we have the Martingale problem, and now we want to also construct solutions to this. So we want to show that if phi is in the domain, so remember this means that phi is K was this operation here, so this modified, the solution to this modified resolvent equation of some phi sharp. Phi sharp needed a certain regularity. The domain was built exactly in this way. And the point is that if we take now such a phi sharp, so such a right-hand side of the resolvent equation, then we can now solve a resolvent equation for the generator of our truncated process. This is phi m. Which we call Km of phi sharp, which is the same sort of equation as before, except that here we have an m. And using all the regularity estimates that we have, it's maybe not so surprising that you can show that this convergence holds in L2. So phi m converges to phi in L2. And let's see what happens when we apply the generator to this phi m. This is L0 of phi sharp plus Gm lower of this phi m, and this converges using the estimates we have for this one, converges to this expression, and that's just L of phi. So in other words, we have found functions phi m such that phi m converges to phi and Lm phi m converges to L phi. Now, yeah, based on that, it's maybe not so surprising that the limiting process, we already know tightness for our processes for these UMs. And now it's not so surprising that the limiting process then will solve the Martingale problem for this domain, right? And I shouldn't have done this. This is the only place I think where I want to be, where I try to be precise about the link between this year's Fock space and this year's the world of random variables. But all the time before and all the time after I identify them. So let's pretend that we just have this phi m and phi here. So we apply this to this process. And since by construction of this is a martingale, and since this converges to this converges to this, and this converges to this, you see that this process is a martingale. There's a small thing.
Nicolas, another question.
Yes. Remind me, what does gamma converge mean? Something with lim sup and lim inf and so, right? So the question
actually,
is,
it's equivalent to what you just wrote. It's convergence of the graphs, if you want.
Of the what?
I mean, I think about gamma convergence as convergence of the graphs of the function of the operators, no?
Right. Okay. Yeah. So this is true. I mean, this is exactly what we show. Yeah.
Yeah, but I'm not sure. Gamma convergence is not that. I mean, it's what the one I know is what Nicolas was telling about, no? In minimization problem. Then there is a link with Moscow convergence, and Moscow convergence is a notion of convergence of operators. But this I don't know very well.
But it's also some lim-inf and lim-sub conditions somewhere.
Yeah, they are related. So gamma convergence and Moscow convergence are related, and Moscow convergence is some convergence of operators. So maybe this is what Milton was saying. But gamma convergence in general is of variational problems.
Yeah, that's why I put it into, you know, into quotes. You know?
Okay.
But anyway.
Yeah, in any case, it's the convergence we need. So that's the good thing.
Yeah, I think it's the convergence of the resolvent, no?
Yeah, exactly. Yeah, for me, gamma convergence is the convergence of resolvents, which is equivalent to the variational formulation if the operators are symmetric.
Okay, but then maybe so, yeah.
Okay. Anyway, so it allows us to do what we want to do. Just one remark about, okay, so technicality. These guys are, of course, not continuous test functions, so they're in L2, right? So everything is just L2. And now this thing converges weakly to this guy, but now you apply non-continuous test functions, so you first have to somehow compare this to a continuous bounded function and show that you don't make an error. And so this is based on the fact that we control, I mean, this thing is stationary for all times. I will address non-stationary in a bit, but at the moment this is stationary, and so you can basically approximate L2 functions by continuous bounded functions, and in this way can pass to the limit. And so we have shown that any limit point solves the Martingale problem for L. Yeah, and now I want to talk about non-stationary initial conditions. So what happens, I mean, yeah, so far everything was for U0 just being the white noise, distributed as a white noise. What happens if we have an initial condition which is absolutely continuous and the Radon-Nikodym derivative is in L2? Then we can estimate any expectation under this measure nu, which is now not white noise. Just writing out what this means, we can write the Radon-Nikodym derivative here and integration against white noise, apply Cauchy-Schwarz, then we get the L2 norm of the density here. And this thing squared, and now we apply Jensen to pull the squared inside. And then we have the 2p here, and now it is integration. I mean, since the squared is inside, we integrate the initial condition with respect to the white noise, so that is just taking expectation with respect to the white noise. So these are the kind of expressions we can control. This is the kind of expression we want to control. And note that this here is really for functionals on the full path space. And this here is just some constant. So all we have to do is pay a price by doubling the p here. This is actually this incompressibility condition which appeared already when we defined the Martingale problem. Actually, in the definition of the Martingale problem, we already assumed that such an incompressibility holds. So everything we did extends to such initial conditions. Some parts would also extend to initial conditions which are in LP for p bigger than 1. Because, well, what would you do then? Then you would just apply not Cauchy-Schwarz, but Hölder here, right? And then you would get just a much bigger exponent here. But it's not true that everything works. So parts of the theory, yes, we can do for LP, for general LP, but then for some parts we really need L2 because effectively we need an L1 control given only an L2 control under the stationary measure. Okay. And this recap, I think I can skip because I did a long repetition at the beginning of the course. So let's now jump right into uniqueness. That's the next goal, uniqueness. And for that, we will go to the Kolmogorov backward equation, and I will show you this new idea of Lukas Grefner, who is a master student, which will, first I show you the old approach, and then I will show you how to improve and simplify that. So we want to prove uniqueness in law for a Martingale problem. And in general, I know two main tools that you can use for proving such uniqueness in law. The first one is Yamada-Watanabe, which tells you that if you have pathwise uniqueness for your problem, so think of your problem as a stochastic differential equation, and think you have some contraction property on path space or some monotonicity or something you can exploit on path space in order to get uniqueness, then through the Yamada-Watanabe condition under suitable conditions, criterion under suitable conditions, you can lift this to get uniqueness in law. However, I mean, this for us, yeah, so actually we don't really know how to prove pathwise uniqueness, right? So we don't hope to be able to carry out this program, at least not at the moment. So rather we go to the second main moment for proving uniqueness for martingale problems, and that's duality. So in duality, you prove basically uniqueness for one process by proving existence for another process, which is a dual. And like this, you can turn a uniqueness proof into an existence proof, and existence proofs are often easier because you can use compactness arguments. And the simplest duality, I mean, well, that's a whole field and people are very interested in very complex dualities, but the most fundamental duality is really the duality with a PDE, with the associated PDE, and that's the Kolmogorov backward equation. So the duality, let me explain the duality on the simplest example of an SDE, and really it's Kolmogorov backward equation in that case. So let's say we have a weak solution to such an equation. And let's say we're able to find a strong solution to the Kolmogorov backward equation, where this here is the generator. So it's B times the first derivative plus 1/2 sigma squared times the second derivative, this operator here. And we find a C2 solution to that. And for a given initial condition phi, so that's the Kolmogorov backward equation, then we can apply Ito's formula to see that phi of xt, this is just since u0 is phi, is equal to ut minus t of xt. And now we let time run. So this is ut minus 0x. And then here we get the time derivative, except that time is running backwards. So we get minus the time derivative. And then plus L coming from this, so the generator coming from Ito's formula of ut minus sxs plus some martingale. Now, yeah, and this thing here is 0 because we have this equation. So this here is a martingale. If we take the expectation, it drops out. So if we take the expectation, we see that the expectation of phi of xt is equal to utx. This means that if we can solve this equation for a dense set of phi's, so we need many solutions to this equation for many phi's. But if we can do that, then all of these expectations are uniquely determined, and therefore the law of xt is unique. Just the law at one fixed time. But then you can iterate this, and after that you see that the law at time 1, the law at T1, T2 is unique, after that T1, T2, T3, and so on. And in that way, you see that the finite dimensional distributions are unique of this process. Again, under the assumption that you can solve this equation for a dense set of phi's. And note that in this kind of argument, we didn't use uniqueness of any of these guys. This was not unique, and this was not unique. We only used the existence for both of them. And you can also go the other way around. So you can also use the existence of the SDE to prove the uniqueness for the PDE, right? At least for those initial conditions where you can carry this program through. Okay, so this is what I said. Existence for U implies uniqueness for X. So let's do this for our problem. So let's take an initial condition in the domain of our operator.
Nicolas,
yes.
Another question in the chat.
Don't we need no unique? So the question is, do we need uniqueness of the equation for U? And the answer is no, because I mean, what if there are two solutions here? I don't care. So then effectively from this formula, we get that any two solutions, if V is another solution, we will have the same identity with V. So that will tell us actually that VTX is equal to UTX. So somehow it comes out of this, no? I mean, at this point, I really didn't use uniqueness at all. I just used that X is a process satisfying that, and U is a PDE's a solution to this PDE. It's okay. Okay.
I suppose you need some control on U to make sure that it's a martingale, not just a local martingale.
Yeah. So this is true. Yeah.
But I have. Can you hear me now?
Yes.
So if we have, suppose we have two solutions to the first equation for x and y, and then we have two solutions for the equation for u and v, then can we have for the last equality two different laws?
No, I mean, then I can first fix the first. Let's say we fix the u. So we take one of these, yeah? So we have u and v, but I just take u. And then I see that by the same argument also we have this identity, exactly the same argument.
Yeah.
So
Okay.
in particular, we have this identity. These two have to be equal. And then we could go the other way around. So now we can say, okay, now we fix this guy. And then by the same argument, we also have that this is equal to VTX. And in particular, these two have to be equal.
Ah, yeah, I see. Thank you.
But it's true that we need, yeah, so here I really mean strong solution. So in the sense that, yeah, in the sense that this thing really becomes a martingale. So let's say this is, yeah, I mean, then you put your favorite conditions. Let's put everything bounded, for example. This is bounded, this is bounded, this is bounded, and then certainly it's true. Right, so can we do the same thing here? I mean, here it's a bit, actually, the argument would even be a bit easier because somehow by definition of the Martingale problem, the thing we get there is a martingale. It is not a local martingale. The Martingale problem says it's a martingale, so we don't have to worry about local martingales. So this is the equation we have to solve for an initial condition in the domain. And the natural idea is, well, we just need existence for that, so we can use a compactness argument. So we could try to solve this equation for some approximation of L and then pass to the limit and hopefully get a strong solution. And now the question is, what does some approximation of L mean? And in our paper on this, we really took Lm, which is really the operator with which we also used for the construction of the Martingale problem, this Galerkin operator. And actually this gives you a bunch of problems because, well, then we said that you get existence of the equation for M through the semigroup. So this is standard Markov process theory, that if you have a Markov generator then and which generates a semigroup, then you can find a strong solution for the semigroup by just for the Kolmogorov backward equation by just applying the semigroup. So just in this way. But the problem is that here we're really mixing up two domains. So for this sort of operator, we defined a few slides ago a domain which is compatible with this sort of domain and then pass to the limit there. But for the solution to construct it through the semigroup, we know that it is really in the full domain of the operator. And actually, it's not even fair to call it Lm, but just somehow the Markov generator of this process associated to the Galerkin approximation, which is some abstract closed operator, which on some nice test functions agrees with our operator. But we don't know if at positive times this thing is still nice enough so that the two agree. So it's actually not the best idea. So in the end, we made this work with a lot of really forcing our way in, and somehow this does work, but it's actually much better to take a smarter approximation here. Not to take this, but to take an approximation where maybe this operator becomes bounded. If this is a bounded operator, then solving this equation here is trivial. You just take the operator exponential and then you try to derive estimates for that. So this is what Kubinelli-Tora did. And yes, admittedly, this is the better solution. Anyways, I will pretend that all these problems don't exist and I will use this Galerkin operator. So now we want to prove some compactness, and the first thing to do is to apply an energy estimate. So we just differentiate the L2 norm, and well, so yeah, you just get this because the derivative of phi m is Lm. Then you split it up, and here you put a minus here, so you have minus L0, which is a self-adjoint operator. So you can put minus L0 1/2 to the other side, and you see that this here is the squared L2 norm of minus L0 to the 1/2 phi mt. And this thing here, well, here you have phi m tested against gm of phi m, but gm is q-symmetric, so you can bring it to the other side and get a minus. And therefore, well, this expression is minus itself, so it has to be 0. So actually this term drops out. And well, this should remind you actually of the energy estimates for the usual Laplacian on the torus, because it's exactly the same thing. Because, well, what is this operator? It's a Laplacian. No, it's just some cascade of Laplacians on larger dimensional tori, but on each torus it's a Laplacian. So of course you get the same sort of energy estimate. And what we get is an L infinity control in L2 and an L2 control in H1/2, because we have this thing here. This corresponds to H1/2 with 0 regularity in N. So the question is, can we also gain regularity in N? This will be important to push this further. And well, to do this, and this is somehow a key point, this will be where we now use some important feature of G, which I mentioned already before. To do this, we just differentiate this sort of norm. So before we were differentiating the H00 norm. So now we put a beta here. So we try to control some regularity in beta, but we don't put additional regularity in the upper variable here, the space regularity if you want. So by the same argument as before, what is the inner product here is just 1 plus n to the beta and then 1 plus n to the beta on the other side. But this again is symmetric, so we can put just 2 beta here. Then we have Lm here. This thing is handled in exactly the same way as before, because the operator L0 commutes with the operator n. Because one is different, I mean, they're both diagonal on chaos. One is differentiating on the chaos, the other one is multiplying the chaos with n. So they commute, and we can write it in this way. So that's great. That's again, I mean, it comes with a minus, so again gives us good control. We can bring it to the other side. What is this here with a GM? Now the argument from before does not work anymore. We cannot bring this to the, well, we can bring it to the other side and pick up a minus, but then things change because now all of a sudden this is inside the G, while right now it's outside if we bring it to the other side. So it is not true that this is skew symmetric in H0 beta. But, well, let's see. So let's split this up. We can split G into G plus and G minus. And now here, what do? I just bring this to the other side. Then we get this term here. And what do I do here? I bring this one to the other side. Then I pick up a minus and a G plus. And this is now acting on this thing with a 1 plus n to the 2 beta inside. But I mean, the G plus takes the nth chaos and maps it to the n plus first chaos. Or expressed differently, what do I see on the nth chaos in this thing here? Something which before was on the n minus first chaos. So this means that I can pull this thing outside and replace it by n to the 2 beta. That's the same thing, just because this one only goes up 1 chaos. And so we get here that, it's not skew symmetric, so it's not 0, but it is this difference here. And just as a sanity check, if the beta is 0, which was the case we did before, then those are the same, right? So they're both 1 and the thing drops out. So why is this useful? This difference here you can bound by 1 times the derivative of this function between n and n plus 1. The derivative of the function gains 1 in beta, so you can bound it by 1 plus n to the 2 beta minus 1. And now this G plus here loses 1 degree of regularity in n, and so everything comes together nicely so that you pick up 2 beta again. And based on this story, we can now control also this expression here. And I guess I have some, So based on this story, with some work, we get such a control. Now H0 beta, beta can be anything provided that phi 0 has this corresponding beta regularity. And then here L2, H1/2 beta, L2 in time. Okay, this is basically, over the rest I will brush very quickly because then I want to present a new approach. So based on this, you can get controlled estimates for the remainder, which is really what we need. So our domain for the operator is parameterized by the right-hand side in this approximate resolvent equation, which was this phi m sharp. And well, if we're given a phi m, then we can always write phi m sharp as somehow we can define it through the equation, right? So it is the right-hand side in the equation if we just plug in phi m into this operator. And then you take the derivative of this phi m sharp. Well, we see here this becomes Lm phi m, and here we just pull the derivative inside, which we can do because this thing is a bounded operator on the suitable space. This we can rewrite in terms of phi m sharp using the structure that we have for this approximate resolvent equation through these 2 terms. And now basically, well, this is now the equation on which we can do analysis. You see we have a sort of heat equation for the phi m sharp, where we have this L0, so we can then use some sort of Schauder estimates to gain regularity in L0 for the phi m sharp. And well, there's a forcing acting on this heat equation, but for this forcing, we have an a priori estimate for this guy. We already have this estimate up here. So we also have an estimate for this term together. And I didn't tell you how to get a derivative for phi, an a priori estimate for the time derivative of phi m, which is not really contained in here. But you can note that since phi m solves the equation, this is the semigroup acting on Lm phi m. And this here is under control by definition. And the semigroup, therefore, is also under control. And like this, you get an a priori estimate for that. And in the end, you can close all your estimates and you get good estimates. And you get a strong solution for the Kolmogorov backward equation. And yeah, so just squeezed in here from that, we get the uniqueness for the Martingale problem. And I think, yeah, exactly. So this is a good place for a break. So let me just recap quickly what we did. We proved uniqueness for the Martingale problem by going to duality with the Kolmogorov backward equation, which we controlled. So we proved existence for that through energy estimates and then controlled analysis of this phi m sharp. And it was very important in the energy estimates that we only lose one here, that we don't lose more. Otherwise, we wouldn't have been able to get anything. And yeah, so that we gained this back by this sort of stupid estimate. What we can also show, which I didn't address now, is that any energy solution solves the Martingale problem. And since we have uniqueness for the Martingale problem through this duality argument, we then also get uniqueness for energy solutions. Okay, and then after the break, so let's take a 10-minute break, and after the break I can explain how we can do things differently and how this allows us to get a little bit of criticality, even to handle a little bit of criticality, and how to do much fewer estimates actually.
Okay, thank you, Nicolas. Are there any further questions? Okay, so let's take 10 minutes break.
So can I just ask, but perhaps, so I haven't fully understood where in your construction for the Kolmogorov equation you have now used the structure of the domain. But perhaps...
So here, right? I mean, so these estimates, they allow you to extract some subsequential limits, and maybe you could even say, I'm not sure, but I mean, it is some regularity. Okay, so maybe you could even say that any subsequential limit of this is some weak solution to the Kolmogorov equation. But to really get a strong solution, we have to work with these phi sharp. So we have to show that this phi m sharp converges to a phi sharp, which is in this H16. Along some subsequence.
I see. So you need the generator really to say, okay, this compactness gives you some object that in some super weak sense will satisfy the equation. But in order to do your duality argument, you need more information, and that's where you
really need. So I mean, Martingale problem is like a weak. So you can also see this whole story with the duality on this level, purely on a PD level. The Martingale problem is a weak solution for the Kolmogorov forward equation, and you cannot close the duality by using two weak solutions. You need one of them to be strong. So we need a strong solution for the backward equation.
I see. And that's why you need to know what the generator actually is for this.
Yeah.
I see. Okay, thanks.
So may I ask a question?
Yes.
So it seems to me that you actually used a little bit of G to get n regularity. I mean, the L0 gives you a lot of regularity for fixed chaos level, but in order to export this regularity to different chaoses, you really need to use the operator G.
So you see, I mean, I brushed very quickly over this part here. I mean, if you see this, I could also write this here now as H0 beta and get rid of this. So you see, the L0 guy doesn't gain any regularity in N, but it also doesn't destroy any regularity in N. The G operator also doesn't gain anything in N. So it's not true that in the end we get more than the beta. So
Okay.
everything will have the same beta regularity as the initial condition. We don't gain anything. But it is quite subtle to see that this doesn't destroy the N regularity. You really have to be careful with this. That, I mean, when you do the estimates naively, then if you're not very careful and use symmetrization arguments and so, let's see. No, actually it should be here. Yeah, then here actually you wouldn't lose N, but N to the 3/2. So, and once you lose N to the 3/2, you're out of it. So you cannot close the estimates anymore because we only gain N to the -1 back from this one. But yeah, so in the end, we only get back what we have in the initial condition. There's no regularization on the level of the N regularity. There is regularization in some, yeah, so there is regularization on the level of this upper index here, because to get this estimate here, we only used H0 regularity in phi 0. Mm-hmm. So this is coming from the L0 operator that we gained something here.
Okay, thank you.
Yeah, so there was a question in the chat being self-adjoint. Yeah, so Martin answered. Right, so the G is Q, so somehow anti-self-adjoint, is Q self-adjoint. So if you bring it to the other side, you pick up a minus. And exactly, so L0, I mean, L0 is a Laplacian. So this is extremely easy to analyze, Laplacian on a torus. And because we know the orthonormal basis and everything, and the orthonormal basis is the one we like the most, the Fourier basis. Is it maximal dissipative? So it's dissipative. This will become important. I don't know what maximal dissipative means. So in any case, this operator so far is not closed. Then you can see once you construct the semigroup that it's closable. And I guess then the closure should be maximal dissipative. Yeah, okay, so it's a generator of a C0 semigroup, which we show basically by solving the Kolmogorov backward equation. Because, I mean, once we have that, this solution, then for such nice initial conditions, then you can extend the semigroup, of course, to general L2 initial conditions, just because the semigroup is a contraction semigroup. So you have a, I mean, if you converge on the level of the initial condition, then the output has to converge.
Maybe as far as I remember, so the generator with the domain you define it, I mean, this operator with the domain you define is not the generator, no, but it can be extended.
Yeah, so it's probably a core for the generator, but I mean, I don't think we checked this carefully.
Yeah, but no, I don't think it's even a core, no, because we cannot restart the Kolmogorov equation. Oh no, yeah.
No, we can, but it was, yeah, this was, this was this thing what I mentioned, that actually this stupid truncation of the operator, which we did in the paper, which I put in there, actually creates a lot of problems, and it's actually not so easy to see that you stay within the domain, but in the end you do.
Okay.
Okay, so are we taking 5 minutes break and continue schedule, or you need 10?
No, 5 is good, because also I will skip probably a few things. I still have like 30 slides or so, I think.
Okay, so let's meet in 5 minutes.
Okay, so this was with a lot of computations, but in the end everything worked and we did what we wanted to do. And by the way, you can also extend all this to the equation on R. So we didn't strongly use the torus in all of this. We used Fourier transform though. So if you would want to go to a like not so simple domain, then things would, or like some boundary conditions also, things would become more complicated and you have to think about it. But R with Fourier series is, Fourier integrals is not a problem. Now let's try to do something else. So to construct the domain, we solved this equation, which was a proxy for the resolvent equation. And sorry, this should be a 1 here. Okay, no, I think it's okay. It was a proxy for the resolvent equation, or actually for the Poisson equation with lambda equal to 0, except that we replaced the g by this g upper here. So the question is, can we do something softer than doing all this analysis for that? And one very stupid attempt is, let's take this equation and try to derive some a priori bounds for the solution. So the solution to this equation is, because this thing here generates a semigroup Tm, contraction semigroup. So you can write this as integral 0 to infinity e to the minus lambda t Tm psi dt. So therefore, we have a bound for the L2 norm of this guy, which is just, well, pull the L2 norm inside. This is a contraction semigroup. So this is based on the stationarity that this is a contraction semigroup. So you bound this by psi, and after that you have this integral, which gives you 1 over lambda. So you immediately, without any computation, have an L2 bound for the solution to this equation, which doesn't depend on M. By a compactness argument, this means we can extract a weakly convergent subsequence, which converges to some phi. And now the question is, does this phi still solve our equation? So can we say that phi plugged into this operator here gives still the same right-hand side psi? And the answer is that this question doesn't even make any sense, because the operator G takes in things which need a minimum regularity. You cannot plug in everything into the G. There was this G minus, for which we needed regularity at least a quarter, or a bit better than a quarter. And this one only has regularity 0, so okay, we cannot even make sense of this question. So this was maybe a bit too stupid. But, well, it tells us we can get some bounds without doing any computations whatsoever. So maybe we can push this further. And this was the idea by Lukas Grefner, who, I guess, so in this paper we do a lot of computations with Fourier series, and I think he tried to avoid doing all these computations with the Fourier series and rather think about it conceptually, and found a way in which we can indeed avoid most of these, or nearly all of these computations. So the problem is we only have L2 control. If we would have some control in some H alpha, even H alpha 0, if alpha would be bigger than 1/4, then this thing would be well defined, and maybe we could even say that this equation holds. Well, so
sorry, so you derive the bound in that way, but you can test on the right-hand side, no? And then you get a better estimate. You can test.
Yeah, so you could say that is a weak solution. That's true. Is that what you're saying?
No, that, okay, you take your equation, you take the equation for phi m, and now you test it against phi m.
Right.
And this gives you a better estimate, because you control also the H1/2 norm. Or I'm wrong?
Yeah, so this is what we did in the energy estimates. No, so that's effectively doing the energy estimates.
Yeah, just on the resolvent equation and not on the parabolic equation. Yeah, anyway.
Yeah, okay. So, and okay, this would give you the same a priori bound.
Well, it will give you also the regularity. It will give you.
Yeah, exactly. So yeah, exactly. Let me present the other way of doing it, but it's giving the same result, yes. So let's transform the problem. Let's call phi tilde just this thing. And if then by some argument we get an L2 bound for phi tilde, then we get automatically, because, well, phi tilde is this thing. So phi is equal to this operator to the -1/2 of phi tilde. We automatically get H1/2 0 as long as we have an L2 bound for phi tilde. So we had this equation. Now I just put a 1 here. There's no point of carrying any lambda. So lambda is equal to 1. And well, you can work it out. So what equation does phi tilde solve? So we have a phi here. This is phi tilde to the -1/2. That's why we get a -1/2 here. And then we hit this thing with the same operator to the -1/2. So principle, we would still see here 1 minus L0 to the minus 1/2, to the plus 1/2, sorry. And to get rid of this, to turn it into a 1, we also hit everything from the left with 1 minus L0 to the minus 1/2. And then this thing here becomes a 1. Here we pick up this term. And of course, since we hit everything from the left with this operator, we also have to hit the right-hand side with this operator. So instead of going to the resolvent equation, we study this equation. And the bound for that, this I already said. So if we bound this one in L2, we bound this one in H1/2. And well, formally, this operator appearing here is skew-symmetric because this one is symmetric. So we bring it to the other side. Then this we bring to the other side, we pick up a minus, and then this again we can bring to the other side. So we see that if we call this t, then when we bring t to the other side, we pick up a minus. And if we consider a bounded approximation, so this is the point. So now we consider a bounded approximation to this operator, which is still skew-symmetric. And in that way, we get that the adjoint of this, so which satisfies this now really as the adjoint. So to make this rigorous, this here was a bit formal, but if this is a bounded operator, then we can make sure that this really holds as the adjoint. And then since this guy is skew-symmetric, you can apply some results from functional analysis, which tell you that the spectrum of that guy is purely imaginary. Okay, what is this good for? Well, we want to invert this operator, where the spectrum of this operator is purely imaginary. And well, that's another general result from functional analysis that Lucas found, that said that if you have an operator which has a purely imaginary spectrum, then this inverse is automatically bounded by 1, no matter what this operator does, as long as it's a bounded operator with purely imaginary spectrum. And it makes sense now, because if you think of just inverting a complex number, so you have 1, which is this one here, and then minus something imaginary here, well, then the norm of this guy is of course bigger than 1, because this is purely imaginary. So you have to add the absolute values of these things, basically, the square root of the squared absolute values. So this is bigger than 1, so 1 over that is less than 1. And so the same thing works also for operators. So this gives us indeed the bound that the solution to this equation is bounded by 1, because, well, this solution to this equation is just the inverse of this operator applied to the right-hand side. And then phi m is the 1 minus L0 minus 1/2, so inverted here. So it gains half regularity, and it is actually, so the phi m is the solution to the resolvent equation. So now we have shown that, what Massimiliano also said, the solution to the resolvent equation has H1/2 0 regularity. So this is bounded up to some constant by 1. So now we can again extract a weakly convergent subsequence, and by compactness, so now here we use the torus. If we're not on the torus, then the Sobolev spaces are not compactly embedded into each other, and you have to go to weights. But anyways, let's say we're on the torus. So then if we give up a bit of regularity, then by compactness, we have strong convergence in this space. So weak convergence in H1/2 0, strong convergence as soon as we pick up, as we give up a bit of regularity along some subsequence to a phi. And so now this operator here is well defined, 1 minus L of phi, because H now has regularity better than 1/4. Well, it has 1/2 minus an epsilon, so 1/4 better than 1/4, which is all we need to control this G minus. For G plus, we can plug in anything. It just loses a lot of regularity, but it is always well defined. But G minus needs a minimum amount of regularity, which we have. And if you write the difference of these two guys, then you can split things up somehow in such a way that each of these terms with the control that we have converges to 0. Both of these convergences are in bad spaces, spaces of negative regularity, but it doesn't matter. So the left-hand side is an element of L2. And what we say here is that it's given as a limit in some weak topology of some distributions which in weak topologies converge to 0. So this means that in some distributional space, the left-hand side has to be 0, but then of course already it has to be 0 as an element of L2. So indeed, we now have a solution to our resolvent equation. So, and this came really for free, no? There was no Fourier computations in here or so. It was really just using the estimates that we have for our operators and then passing to the limit here. This was for one test function, right? So we had right-hand side for our equation. Then we solved some approximate equation with an m here basically, and had the phi m's, and then we passed along a subsequence to a limit, and then we had one phi along one subsequence which solves this. But now you can use the fact that the space is separable and work a little bit and show that actually that this converges along one subsequence for all psi. And this is again weakly in h0 1/2 and strongly in h 1/2 minus epsilon. So let's call this limit a of psi. Then by what we saw, I mean, this is just this claim here. So this here is our a of psi. So 1 minus L of a of psi is equal to psi. That's this thing here. And so therefore L of a psi, well, bring this to the other side, is equal to a psi minus psi, and it is in L2. So we have constructed a domain. So this is a d tilde. It's not the same domain as before. This is just a psi for all psi in h0, 0. One remark is the operator L that we work with is defined independently. The operator L is still L0 plus G. It's the operator defined on Fock space that we started from. This whole construction with a subsequence that we extract, and then we have some weak convergence and so, is just for finding these functions on which the operator behaves nicely. But the operator in itself is, as a thing mapping to distributions, was given before, and it did not change. It does not depend on the subsequence. So we only use it to define a domain. And now there's this magical variant. So at first I didn't understand what the difference of this with the Hilly-Yoshida theorem is. So this is some variant of the Hilly-Yoshida theorem. And there's one magical ingredient here, which I'll comment on in a second. So the theorem is, if we have a Hilbert space and a linear operator on some domain on this Hilbert space, which is dissipative. So it means that the eigenvalues are negative, basically. The spectrum is negative. So LH tested against H is negative for all H in the domain. And there exists a lambda such that this map is surjective, so that you can solve the resolvent equation for any right-hand side in your Hilbert space. Then automatically your domain is dense, and this operator generates a contraction semigroup. And so the magic is that you automatically get the denseness of the domain. So if you look in Ethier-Kurtz, then the theorem, what they call the Hilly-Yoshida theorem, would have a third condition here, which says that third d of L is dense, and then you get this property. But the magic of this theorem is that if you have a Hilbert space, or more generally a reflexive Banach space, then you get the denseness of the domain for free. You don't have to check anything. So this part here is exactly what we want. Now we want the domain to be dense. This we need it in the Martingale problem, we need the domain to be dense because we need this set of test functions to identify the one-dimensional margins and then the n-dimensional margins of our process. Then we need a dense set of test functions. So we need this thing. And we, of course, need a strong solution to the Kolmogorov equation, Kolmogorov backward equation, which is exactly this thing here. And we already know the second property in our case, well, because we solved this thing here for any right-hand side. We solved 1 minus L, A of psi is equal to psi for any psi in gamma L2. So we have this one also for free. It's not just that the resolvent is dense, the image of it is dense, but it's really the full space. So the only thing that's left to show is the dissipativity. After that, we have the denseness of the domain and the semigroup. Okay, so yeah, dissipativity, maybe I can skip this. In principle, the idea is to split this off into L0 plus G and then use the fact that L0 we know it gives you something negative, and G is skew symmetric, so it gives you 0. This does not work quite on this level, but so you approximate things and use the fact that the norm of for a weakly convergent sequence is less, that you have this Fatou property is less than the lim inf. And in the end, you can reduce it to the dissipativity of the operator L and K, which is fine. Okay, so we have dissipativity. Now, this whole argument was not perturbative anymore, right? We made a little bit use of this operator L0, but we didn't really see that now the operator is a perturbation of L0. So let's try to see how far we can push this. Let's try to take a more singular model. So we take the fractional Burgers equation.
Can I ask a question, Nicolas?
Yes.
So is it the only thing that you really used here to say you have a self-adjoint operator and an operator whose spectrum is purely imaginary, and then you can basically define their sum? That's sort of what you're saying?
No. Then you can find that. No. I think it's more than that. So there was this, we have this convergence. So this part here, there was something quantitative on this level, right? So we have the convergence in this space here, where we lose a bit of regularity. And we need this to be good enough to pass to the limit in this operator. So the convergence is good enough to justify that this thing here converges to 0.
Nicolas, I'm also confused about this point, because somehow, as you said, the operator exists because it's the operator you need in the Martingale problem, so you cannot somehow you cannot change it. How you identify, and the operator is made by two parts. It's made by L0 and G.
Right.
And somehow you see how you identify, so this approximation argument, how does it work? Because
so you just split up L into L0 and G.
Yeah.
And so here for L0, it's no problem. L0 is a continuous operator from h1/2 minus epsilon to h minus 1/2 minus epsilon. And here minus epsilon with minus epsilon at the bottom. So you have, this is a continuous operator, so you have convergence in some very bad space, right?
Yeah.
And then you have G. In G, you have G plus. G plus is a continuous operator from h1/2 minus epsilon to h minus 1/4 minus epsilon. So also this thing. So also it's a continuous operator. It can pass to the limit. The only subtle thing is the G minus. G minus is only a continuous operator on spaces with sufficient regularity.
Yes.
And so there we need that this 1/2 is bigger than 1/4. And this is basically the next point that I'm trying to make. So once we go to fractional equations, we can make these two go closer to each other. As long as this one is bigger than this one, things are still fine.
But is it fair to say that this last point is then again a bit perturbative, to say that the L0 gives you enough regularity to then be allowed to apply the other bit?
Well, so you need the L0. So this is, yes. But we don't really see it as a perturbation. And in fact, this, what I'll say now about the fractional one, you do get existence in supercritical regimes. Not for not for the Kpz fixed point, so not just removing the operator, this does not work. But you can go to the same regime where we know that energy solutions exist, which is a certain supercritical regime.
Yeah, okay. So because you need this epsilon to have the compactness yet, no? So that's, you need some space. You cannot...
this you mean?
Yeah. You... Yeah, because from, okay. Okay, yeah, thanks. It's clear.
Okay.
Sorry.
by the way, this is the story does not give you. I mean, there are some things which you don't get from the story, and we need to do something else after that. So I'm a bit pushing the time, but let's see. Okay, so let's try to push it for this fractional Burgers equation. There should be a square root 2 here, which I forgot. So theta, for theta equal 1, we have basically the same model as before, because this here you can then understand as a first order derivative. And then, well, this equation has the same generator as before, except that the L0 is now replaced by L theta. And L theta is doing the same thing that the L0 did, it's just applying the fractional Laplacian on each chaos, except that we apply the fractional Laplacian in such a way that we somehow do this tensorization, or how you want to call it. So first in the first variable, then plus in the second variable, and so on, plus in the nth variable. And it leaves the chaos invariant, so it's diagonal, and yeah, has the same nice properties, except that we have this theta here. Let's redefine our function spaces, because it's convenient that we put the theta here. Right, so before the function space h alpha beta had a 0 here. This was the space in which we defined it. And now we put the theta to see that the space in which we gain 1 degree of regularity from this operator is exactly h1. Yeah, where we can give up 1 degree of regularity. What kind of estimates do we have in these new spaces? So before we had estimates of this type, where there was no theta, so theta was equal to 1. So we saw that we lost 3/4 of regularity by the operator g minus. Now we lose 3/4 theta. And the same for the g plus. And this is under the assumption that alpha is bigger than 1/4 theta. So before it was alpha had to be bigger than 1/4. And for this one, alpha has to be less. So we have a maximum amount of regularity that we can get. Alpha has to be less than 1/2 theta. And this actually okay, just very quickly, I made a mistake in what I was telling before. In the previous weeks, I always claimed it was less or equal. And I was confused that the whole analysis came so nicely. And so with so few nasty frictions. And if the fact that you cannot take equal here creates some frictions, then you have to do more computations to overcome that. And I remember now why we had to do them in the paper, because exactly you cannot have equal here. Anyways, so we have this estimate. And now let's try the same construction of the operator. You get, because we redefined our spaces, we get again the same sort of bound. We get a bound in h1/2. So we get convergence in h1/2 minus epsilon, except that now we need this one, it's here. We need regularity at least 1/4 theta to pass to the limit in this sort of sequence. Now this means we need 1/2 minus epsilon to be bigger than 1/4 divided by, yeah, so bigger than this. And so you can ignore that, of course, and you see that theta has to be bigger than 1/2. And so this is exactly the regime where in this work by Max and Milton, they constructed energy solutions. So for which we know the existence of energy solutions. So we have a construction of a semigroup exactly in the same parameters, regime of parameters where we have existence of energy solutions. Yeah, so let's summarize this. So we have this exactly, energy solutions theta bigger than 1/2, and this dense domain and the contraction semigroup also for theta bigger than 1/2. And the equation is critical at theta equals to 3/4, which you can see from this sort of estimates. For theta equal to 3/4, we lose 1 degree of regularity from G, and we gain 1 degree of regularity from L theta if we invert it. So the two scale at the same way in some sense. It is not true, or we don't know if these two constructions have anything to do with each other. We have now two ways of constructing certain objects. So one is we construct energy solutions, and the other one is we construct the semigroup. Is it true that we have uniqueness for energy solutions and that this semigroup we constructed here describes the law of the energy solution? We don't know. We don't know if there exists a Martingale problem for this new domain. And we don't know uniqueness for the Martingale problem. We don't know existence, we don't know uniqueness. So all these questions are open, and they're all open because we don't have any control whatsoever in the n variable. So on this Fock space, we can do all these nice computations, and we can go to distributional spaces and so. But once we want to create a link with the world of random variables of processes, we have to make sure that the regularity also in the n variable is positive. We cannot then have something with negative regularity there. And well, once you apply the operators in these kind of things where we have some h1/2 0 regularity, and then you apply the operator and you pick up some minus epsilon or maybe minus 3/2 minus epsilon or so, you cannot go back to the world of random variables and you cannot really do anything. And so this was Lucas's second idea, and I can try to explain that in 4 minutes. Well, let's just iterate the first idea now. So the first idea is you apply this operator to the solution of the resolvent equation and call this thing phi tilde, and then prove some estimates for phi tilde. Now let's call phi double tilde the thing where we also apply this operator. Then, well, this is the resolvent equation. Let's see what kind of equation this phi double tilde solves. We have to invert this operator before taking the g, because what we plug into the g is the phi. So this is this thing brought to the other side with a minus of phi double tilde. And now we want to again turn this thing here into a 1. And for that, we have to apply this operator from the left with a plus beta here and a minus 1/2. Because from the right, we have minus beta and minus 1/2. Then we have 1 minus this guy. So we need another one of this minus 1/2 here to get rid of this thing. And then the beta here to get rid of this thing. And then this becomes a 1. And then we have the phi double tilde. And then on the right-hand side, we just have this. Because we just plug the same operator. We apply it from the left. We apply it also to the psi. Okay. Now the problem is that this operator here, because of the beta, unlike for beta equal to 0, is no longer skew symmetric. So the soft argument of saying that the inverse of this operator is bounded by 1 doesn't work anymore. We need to do something more. We need to now get our hands dirty. And this was also a theorem that Lucas dug up from the book by Kato, I think. This is perturbation theory, which tells you that you can, well, if you can understand this sort of operator as a perturbation of a skew symmetric operator, then you still have ways of getting bounds for the inverse. And we can do this if somehow this whole thing here is a bounded operator, maybe a small bounded operator. So all of this here should be okay, it's a bit confusing how I tell it. Yeah, so I don't have much time, so let me just somehow on a very bird's eye level. So the idea is this gains us some regularity from this operator. We have to bring this out basically to make this skew symmetric. So if we would take this out of the G, then it would cancel with this thing and it would be exactly the skew symmetric operator that we already know. Bringing this out of the G, as we saw before by this Taylor expansion of the function 1 plus n to the beta, gains us some regularity in n. And so if we know that G loses at most 1 degree of regularity in n and 1 degree of regularity in L theta, then we can see this as a perturbation and use some perturbation theoretic result to tell us that the inverse is still bounded uniformly in M, and then you can carry the whole process through. So if G loses at most that, and we can gain a small factor, then we control the n regularity through a perturbation theoretic result. And once we have the regularity in n, we already have the regularity in the other variable. Once we have the regularity in n, let's be a bit careful there. We expect that we have existence and uniqueness of solutions to the Martingale problem. And Lucas already proved that any energy solution then solves the Martingale problem and is unique. At least uniqueness, I'm not sure if we showed that it solves the Martingale problem, but proved uniqueness for energy solutions. And now we just have to combine this with or compare this with the estimates we have. So this one loses 3/4 divided by theta. And here we lose 1 degree of regularity in the the n variable, and the same in the theta variable. And so this is okay. we may lose this much, so that was fine. This thing here is okay if theta is bigger than 3/4 or theta is equal to 3/4. If theta is bigger than 3/4, then you can actually somehow, by refining the analysis a little bit, force a small factor. Basically, you still have a bit of regularity left to play with, and you can create a smallness condition out of this. If theta is equal to 3/4, then there's nothing left. We lose 1 degree of regularity here, and we gain 1 degree of regularity back from these two guys. So everything balances exactly to 0. There's nothing left. And we need a small factor for this perturbation theory. So we need to force this. So we need to change the operator to L theta plus epsilon times G. Epsilon could be either sign, but it has to be an absolute value less than some epsilon 0. If this is true, then you have this smallness condition and you can apply the perturbation theory and get the bound in N and then carry everything through. And so this is in the end the theorem you would get. And I think at least until here, well, not everything of this is a theorem actually until this point. But so we look at this fractional Burgers equation again with square root 2 here. And if theta is bigger than 3/4 or theta is equal to 3/4 and the epsilon is less than some epsilon 0, then there exists a dense domain for the generator. You can find a strong solution for every function in the domain to the Kolmogorov backward equation. And if you have an initial condition which has a density in L2, you can find a unique energy solution. So this is true. This one, let's ignore this. I'm not sure if this is true, but you can find a unique energy solution to this problem. What is open is if this energy solution in the critical case is Gaussian or not. This we don't know. We discussed this, I think, in the first lecture. Yeah, and just a remark, so these sort of models arise as scaling limits actually of certain long-range asymmetric exclusion processes. And I think, I'm not sure if I remember correctly, but I think in this case, actually, it's not weakly asymmetric, but it's just, you don't tune the model, you just scale out and then you can generate this equation as a scaling limit. So an energy solution to this equation as a scaling limit. So this was work by Patricia and Milton. And so I'm a bit over time, I had this prepared here that you easily get a spectral gap from all these considerations, but maybe let me not overstretch this too much. And I had all these recaps in between all the lectures, so let me also not do a final recap, but let me just stop here and say thanks.
Okay, thanks, Nicolas. So maybe we can, if it's possible, to unmute everyone. Give a big round of applause. And are there any questions?
Can I ask much more about this triviality? I mean, you sort of already alluded to this in the end. So can you do this for the 2D Kpz equation that that Dirk and co looked at?
And then leave. I guess this isn't as big of an issue.
Giuseppe answers no.
Okay.
No, because I think that in 2D, it would correspond to theta equal to half. So for example, in 2D Kpz, you don't even have, so I mean, if you notice, like in 1D, for theta greater than a half, you already know that by the Ito trick, you have boundedness.
Mm-hmm.
While in 2D, this is not true anymore. So you need some factor in front of the nonlinearity.
Mm-hmm.
Yeah. So it seems, so it's true that also in other models, the construction of the semigroup in this way where you don't control the n regularity, so where you cannot go back to random variables, works for the same regime where the construction of energy solution works. And so this may be supercritical in some equations. So also for this, so this is what Lucas was looking at, the quasi-geostrophic, surface quasi-geostrophic equation. It's the same thing. So the equation is critical actually at theta equal 1, so where you just have a usual Laplacian. And construction of energy solutions works for every theta bigger than 0. There was this recent paper by Tots. And construction of the semigroup also works for every theta bigger than 0. And I think the same is true for these hyperviscous Navier-Stokes sort of equations.
Nicola, yeah, I'm still confused by the beginning because so it seems, yeah, as Hendrik observed, very general. So when at the beginning you say you approximate G by a bounded operator, what do you mean exactly?
So for example, you just have to make sure that everything is still skew symmetric. But so you could truncate the chaos and the Fourier modes. Just you truncate all Fourier modes, which in absolute value are bigger than M, and you truncate all chaos is bigger than M, and you apply this before and after G. So this would be one way you could do this.
But then it's not antisymmetric anymore, no? I think
because you do it before and after, it will be antisymmetric.
Ah, okay, yeah. If you do on both sides, yeah. Yeah, okay, I see. Yeah, because I'm puzzled, no? I mean, this uses only that it's...
No, but in the middle, still I will have a high temperature point.
Stefano?
Yes?
Okay.
What happens?
I don't know. I know that Milton had a question. Milton, are you there?
I'm here, yes.
Okay, please.
So just let me clarify, because you know this uniqueness of energy solutions was somehow preventing a lot of results in the particle systems world to be proved. So you're claiming that, for example, the quasi-geostropic equation, this works for the usual Laplacian in the quasi-geostropic equation.
Under smallness, if there's a small factor in front of the nonlinearity.
And also and what about 2D Navier-Stokes?
Yeah, so then there's the question which noise you take and which measure you take. So there's this, if you take the, I think the free field for Navier-Stokes, so which means like white noise for the entropy, for the vorticity, then this is classically well-posed, so there's no problem there. And you can even forget about the Laplacian. You cannot take any noise. You can just look at Euler's equation. Okay, this is then not, you don't know if it's well-posed, but you can construct solutions to that. So the operator G basically in that problem is well-defined by itself. So Flanduli has done a lot of nice work recently on that. And then there's this other measure, which I think it means it's white noise basically under the Navier-Stokes equation. So this means on the level of the vorticity, it's something horrible. And there's this work by Max with Mathiatura where they get uniqueness for fractional theta bigger than 1. And I think this method should, but I mean, I don't think Lucas or me looked into that, but so somehow from the message that you get that now you can always push it down to the critical value, it should be possible to get also now the theta equal to 1 as long as there's a small factor in front of the nonlinearity.
I don't know if they fit into this theory, but there are these Keller-Siegel systems which are similar to the quasi-geostropic equation.
Yeah, I mean, the name rings a bell, but I cannot say anything qualified on that.
Okay, thank you.
Sorry, but for Navier-Stokes in 2D, would the, like, and let's say theta equal to 1, so the Laplacian, the usual Laplacian, I mean, would the Ito trick work in that case?
Yeah. So
what was the question?
So does the Ito trick work for 2D Navier-Stokes and theta equal to 1?
Yeah, so you mean under this, so under the white noise measure for Navier-Stokes, which is like this horrible measure for the entropy. I
remember in the paper with the, I think we did it in the paper with Jara, and no, it does not work, if I remember correctly. But,
So that somehow you see a logarithmic explosion at that
yeah,
point.
it's like to DKP. So is the
Yes, that's the,
yeah, this is actually a weird case, not because in this case you have actually uniqueness in the same regime where you have existence of energy solutions, right?
yes,
Yeah.
exactly.
Yeah, no, I think there is something we don't understand about this business
Because I think it's the same as in 2D Kpz, so that somehow also there maybe there is the need for some log in order to normalize in order to tame the nonlinearity. That's it.
Yeah, but for example, you see, if you take Euler, you have existence. But okay, there is no way to have uniqueness. So it's really.
But no, Euler, you have existence under the other measure, no? So under the.
Yeah, but I'm saying, okay, you can have like existence, but so somehow the two thresholds are very different from each other.
Okay.
Like for Kpz, you have 1/2 and 3/4. You see what I mean? Maybe?
Yeah.
But so if you, this I was also wondering. So if you take the entropy measure and you put now some fractional Laplacian, some theta, I'm not sure. I think you might. So you have existence for theta equal to 0. I'm not sure at which point you have uniqueness.
Yeah,
so it could be that. So for theta equal to 1, this is somehow classical, right? And you even have pathwise uniqueness. I'm not sure if you could have like weak uniqueness already for theta equal to epsilon. I'm not sure.
I don't remember. Yeah, I never did this computer. This could be interesting. I mean, somebody would have to do it. But still, you cannot.
So I'm a bit. So there's a question if I could provide a link to this. So I'm a bit. I kept it also a bit vague. So this thing is not. Does not exist yet. He will submit his master thesis August 1st, I think, something like this. So then it will be written down. And I don't know. You could ask me if I could ask him if he would be willing to provide his master thesis.
Notation is too difficult mathematically. So we have a very good agreement between the analytic prediction.
Sorry, I think I interrupted Max, or?
No, I was not. Yeah, okay. I was not speaking very much. Yeah, I was wondering. Yeah, somehow like Julia, I was wondering since it's now start to be very abstract. There is no explicit domain anymore. So I was wondering if it's something it's known, like this sector condition or graded sector, whatever, at the end of the day, because it seems very.
So it's not the graded sector condition. This we checked for the paper, but it's of course strongly related. So for the graded sector condition, you cannot lose 1. You have to lose less than 1.
No,
right?
But in your computation, this never enters somehow at the beginning, no?
Well, I know what you cannot lose 1 because you did something more clever. Because what they did is that they solved the elliptic problem. That's why they cannot lose 1. So you're losing the parabolic problem, and you can go up to 1 because actually your bounds they blow up in time.
No, I don't.
Yeah, but no. But even on the resolvent equation, so this last argument was on the level of the resolvent equation. So there, so there you can also make use of this.
Yeah, as far as I understand, whether you look one or the other, you get always the same result. And I don't know a situation, unless if you cannot, of course you can solve the parabolic equation for small time, but if you insist you want to solve for all times, it's like resolving the elliptic equation. There is no much difference.
Yeah, but I mean, in this graded condition, you need to send the lambda to 0.
Yeah, maybe this is the point, because Right, so when people do this, they're interested in large scales. While here we effectively are interested in small scales. I mean, we want well-posedness theory, and then studying the process would be a second step. Right, and since you can send lambda to infinity, you can actually gain a small factor from, I mean, it's not really, you don't have to only see 1 plus n to the minus 1. You can actually replace this by lambda plus n to the minus 1. Then lambda is huge, and this then actually gives you a small factor, which you can use in this perturbative argument. So the comment by Julia that it looks like the Billman-Schwinger principle, I don't know, but I would be very interested if you could somehow give me a reference on that. That also, I don't know. I've never heard this, so I cannot really say anything about it, but I would be definitely interested to hear about it or to discuss about it.
Are there more comments, questions? Let's give everybody the chance to type something if they want to, but doesn't seem to be the case. So perhaps let's just, wait, I have to allow everybody to unmute themselves. Did I do that now? Yeah. Oh no, sorry, I just muted everybody. So fine, sorry, I did it the wrong way around. So now let's just thank Nicolas one more time for for these really nice lectures and for making the effort to teach, even though he had to teach so much in the last weeks, and to sit down and do this for us. It's been great. Thank you very much.
Thanks very much for this nice school. I'm sorry that I didn't manage to attend all the courses because we still have these exams and so, but it's very interesting.
Thanks very much. So it's been very nice. And so I stop the recording and